Have you ever wondered how we can get a massive amount of power from something so small you can't even see it? Well, that's the magic of nuclear energy. Today, we're going to take a journey right into the heart of the atom and then build our way up to a full-scale nuclear reactor to see exactly how it all works. So let's jump right in.
All right, here's our game plan. First, we'll look at where this power actually comes from, the atom itself. Then, we'll see how one tiny event can snowball into a massive chain reaction. After that, we'll explore how we keep that reaction under control, what kind of fuel it uses, and finally, we'll put all the pieces together to see the whole nuclear powerhouse in action.
So first things first, where does all this incredible energy actually come from? Well, it's not like burning coal or gas. No, this power is hidden deep inside the very building blocks of matter. We're talking about the atom.
Okay, so you probably remember this from science class, right? You've got your nucleus in the middle, packed with protons and neutrons, and then you have electrons zipping around the outside. Now, most of the chemical reactions we see every day, like fire, just mess with those outer electrons. But nuclear energy, that's a whole different ballgame. It's about tapping into the colossal energy that holds that tiny little nucleus together. Now, there are two main ways to get that energy out. You've got nuclear fusion. That's what our sun does, smashing light atoms together to make heavier ones. But then you have its opposite, nuclear fission. And that's all about taking a big, heavy atom and splitting it apart. For the power plants we use today, fission is where it's at. That's the key to everything we're talking about. So when one of these heavy atoms, like uranium, splits, two things happen. First, you get a huge burst of energy. But here's the really important part. It also spits out 2 or 3 extra neutrons. And these little guys, well, they're the secret ingredient for creating a power source that can run itself. They make everything else possible. So what's the big deal about a few stray neutrons? Well, they don't just fly off into nowhere. Each one of those neutrons can go on to start another fission event, which creates more neutrons, which creates more fission, and suddenly you've got this incredible cascade of energy. You've got a chain reaction. The best way to picture this is like a set of dominoes. A single neutron comes in and bam, it knocks over uranium nucleus. That nucleus doesn't just fall, it splits and throws out a couple more neutron dominoes. And they go on to knock over other uranium atoms. Before you know it, you've got this expanding, self-sustaining reaction releasing a tremendous amount of energy. But an uncontrolled domino cascade sounds kind of dangerous, right? So how do you control it? It all comes down to one crucial number that engineers live by, the multiplication factor, which we just call K. Think of K as the growth rate for our neutron population. It simply tells us if the number of neutrons is growing, shrinking, or staying exactly the same from one moment to the next. It's pretty simple, really. If K is less than 1, you're losing more neutrons than you're creating, and the reaction just fizzles out. That's subcritical. If K is greater than 1, the reaction grows bigger and bigger, exponentially. That's what happens in a bomb, and definitely not what you want in a power plant. The sweet spot, the absolute goal, is to keep K perfectly at 1. That's called the critical state, where the reaction is perfectly balanced, stable, and just keeps on going. Now, getting to that perfect critical state isn't just luck. It's an incredible feat of engineering. So let's pop the hood on a reactor and look at the clever tools that are used to tame that chain reaction and keep it in that perfect Goldilocks zone. You've got 2 main players doing this job. First are the moderators. See, the neutrons that pop out of fission are moving way too fast to be effective. So moderators, like plain old water, act like speed bumps to slow those neutrons down to just the right speed to cause another fission. Then you have the control rods. Think of these as neutron sponges. They're made of materials that just love to soak up neutrons, taking them out of the game entirely. The control rods are really the driver's seat of the whole reactor. You push them further into the core, they soak up more neutrons, and the reaction slows down. You pull them out, more neutrons are free to do their thing, and the reaction speeds up. They're the brakes and the accelerator, giving operators pinpoint control over the whole system. Okay, we know how to start the reaction and how to control it, but what are we actually using for fuel? Let's take a look. And while we're at it, we're going to touch on a concept that sounds like it's straight out of science fiction. It's called breeding, and it's all about creating new fuel. So when you dig uranium out of the ground, you get a surprising mix. Get this. Over 99% of it is an isotope called uranium-238, which, for our purposes, doesn't really work. The stuff we actually need, the fissionable uranium-235, makes up less than 1%. It's incredibly rare. That's why the fuel has to be enriched, a process that just bumps up the percentage of that all-important U-235.
So why go through all that hassle of enrichment? Well, the payoff is just staggering. The amount of energy packed into a single kilogram of this fuel is the same as what you'd get from burning 4,500 tons of coal. Just try to picture that. It's an unbelievable amount of power from a tiny amount of stuff.
But hold on. What about that 99% of U-238 we said was useless? Well, what if it wasn't? This is where fast breeder reactors come in. These amazing machines can actually use some of those spare neutrons flying around to turn that useless U-238 into a brand new, totally usable fuel, plutonium-239. Let me say that again. These reactors can literally create more fuel than they use. All right, we've covered the physics, the chain reaction, the controls, and the fuel. Now it's time to put it all together. Let's step back and look at the main components that make up a real working nuclear reactor.
So really, every reactor comes down to these 5 key parts. You have the core, that's where the fuel lives and the chain reaction happens. You have the moderator, slowing down the neutrons. You have the control rods, acting as the brakes. Then you need a coolant, usually water, to grab all that intense heat and carry it away. And finally, you wrap the whole thing in massive biological shielding, like super thick concrete, to keep everything safely contained. That heat then just boils water, the steam spins a turbine, and you get electricity, just like in a regular power plant.
And that brings us to the big question, the one that engineers and policymakers are grappling with right now. This idea of a breeder reactor, one that makes its own fuel. It sounds like the Holy Grail, right? A source of almost limitless clean energy. But is it really that simple? Or does this incredible technology open up a whole new can of worms, with its own unique safety and security challenges to solve? That's the conversation that will really define the future of nuclear power.